Doublet antenna is a form of dipole antenna with a balanced feeder like an open wire feeder or ladder line used along with an antenna tuner to provide multi-band operation. VU3 TPW is using a doublet antenna to cover HF bands from 80 meters to 6 meter. Open wire feeder can operate with standing waves along its length and effectively becomes part of the antenna, enabling operation over a wide range of frequencies. As the two wires in the open wire feeder carry equal and opposite currents, their radiation cancels out. Doublet antenna is popular among radio amateurs who wish to cover several bands with a single antenna. Basic principle is that each half of the top and each wire in the balanced feed line must be of equal length. Antenna top is cut to resonate at any particular frequency to suit the location. Typical length of one section of the top section is quarter wavelength of the lowest frequency one is planning to operate on. Hence, it will be 20 meter each if you are planning to operate from 80 meter upwards. It has been mentioned that top section lambda by 2 can be reduced in length to about 3 lambda by 8, retaining good efficiency. As the impedance of this antenna can be over a wide range, an antenna tuning unit with a wide range and a balanced output connection is needed. Otherwise, a balun is needed along with the antenna tuner to transition from unbalanced to balanced line. VU3 TPW has used 4:1 and 1:1 balance in series, connected to 1.5 meter RG213 cable leading to the antenna tuner. It is worth remembering that a balanced open wire feeder cannot run through a building and needs a transition like the RG213 cable into the building. If the combined length of one limb of the doublet antenna and the feeder is an odd multiple of the electrical quarter wavelength of the frequency to be used, it has the best impedance match. Typically, it will be 50 ohms, mostly resistive. Dipole antennas can be made physically shorter than the usual half-wave dipole antenna by adding loading coils. It is useful for single band operation with narrow bandwidth. Of course, it is a trade-off between performance and fitting a dipole into a shorter available space. The loading coils have resistive and reactive components of impedance, which can cause loss of RF power in the form of heat. Though this may not be critical while transmitting, loss of received signal power may mean that weak signals may be totally lost. For better efficiency, the loading coil should be nearer the far ends of the shortened dipole, but that would need a larger inductance, which may be technically difficult to implement. Thinner wires for the loading coil would mean more resistive loss of signal. Coils wound on plastic formers are inferior to those wound on glass or ceramic in terms of loss of power. An ideal loading coil would be an air-wound one without any former, which is practically difficult to implement. Physically shorter antennas with respect to the wavelength will need larger inductance for the coils. Inductance required depends on the total length of the antenna, distance from the center to the loading coil, diameter of the radiating wire elements, and the required operating frequency. Ideal coil is one which is made of solid copper and having a length equal to its diameter. Hexbeam or hexagonal beam is a directional HF antenna popular among amateur radio operators for DX work and contests. 83K group of contesters for CQWPX contest 2023 from National Institute of Technology Karnataka had used Hexbeam for higher bands. The name comes from the hexagonal outer shape of the antenna. It looks like an upturned umbrella as well. In the original design by Mike Traffy N1HXA In 1996, both director and reflector had W shape or M and W to be more specific. The revised shape by Steve Hunt G3TXQ is shown in the figure with reflector half of a hexagon. The bending of the driver and reflector reduces the turning radius of the whole antenna compared to the Yagi-Uda antenna, which also works on the same principle. Lesser size would mean a lightweight antenna with obvious advantages on the mast and rotating infrastructure, avoiding the need for a hefty antenna tower. Multi-band Hexbeam antennas covering multiple bands like 20, 15 and 10 or more are popular. In multi-band Hexbeam, the elements for the lowest frequency are at the exterior of the antenna. Vertical spacing between the elements is critical as multi-band elements can influence each other if the elements are not parallel. Figure shows only elements of a single band for simplicity. Supports are made of non-conducting material while the elements can be of insulated copper wire. Hexbeam has a gain of 5 to 6 dBi and forward-reverse attenuation of up to 20 dB. Beverage antenna, also known as wave antenna, is a long-wire receiving antenna invented by Harold H. Beverage in 1921, the name being totally unrelated to a beverage. Beverage antenna is used in amateur radio, shortwave listening, and for long-wave radio DXing. It consists of a horizontal wire which may vary from one half wavelength to several wavelengths suspended above the ground with feed line to the receiver attached to one end. The other end is terminated through a resistor to the ground. The wire points in the direction of the transmitter whose signal is being received from the resistor terminated end. Beverage antenna is ideal for reception of long distance sky wave transmissions from stations over the horizon which reflect off the ionosphere. Excellent directivity and wider bandwidth than resonant antennas with ability to receive distant transmitters is an important advantage. Obvious disadvantage is the large physical size covering a lot of land area and the inability to rotate for changing the direction of reception. Multiple installations are often used to provide wide azimuth coverage. The value of the resistor used for termination is 400 to 800 ohms, equal in value to the characteristic impedance of the antenna. A balun is used at the receiver end for impedance matching. Directivity of the antenna increases with its length from quarter wavelength to about twice the wavelength. Gamma impedance match for the antenna is also known simply as gamma match. In case of a Yagi-Uda type of antenna, it allows the driven element to be a single rod or tube without being cut at the feed point, giving more physical integrity to the system. As the RF voltage at the center of a half-wave antenna is 0, the outer sleeve of the coax can be connected here, which corresponds to the position on the boom as well. The central conductor of the coax is then connected beyond the center point through a capacitor to tune out the inductance of connecting arm of antenna. The name gamma match comes from the resemblance of the shape of connection region to the Greek alphabet gamma. As the gamma match forms an unbalanced system, it can be connected to the coax without a balun, as both the coax and the antenna are unbalanced in this case. Capacitor in the circuit is initially a variable capacitor which is replaced by a corresponding fixed value capacitor after tuning. Gamma match is often used for an HF antenna and sometimes for a VHF antenna. When fed by a 50 ohms unbalanced coax feeder, length of the gamma rod is about 5% of the wavelength. Its diameter is typically half that of the driven element. Spacing between the gamma rod and the driven element is about 0.7% of the wavelength. Value of the capacitor will be about 7 picofarad for a meter of the wavelength. Phased array antennas are those in which the radiation pattern of the antenna can be changed without physically moving the antenna. For the ham radio operator, it would be quite interesting if you can steer the beam without the need for an antenna rotator. The same principle is used in ultrasound imaging to steer the ultrasound beam. If several antenna elements are fed from the same transmitter with a phase shift, the direction of the beam can be changed by changing the phase shift. This is possible when a computer controls the phase shift to each element. It is widely used in the field of radar imaging. In the illustration, computer-controlled phase shifter changes the phase of the signal fed to each element. The progressive delay in signals would in effect change the direction of the superimposed signal wavefront to an angle depending on the phase shift given. By altering the phase shift, the angle theta at which the beam is radiated can be changed without physically rotating the antenna. This is a one-dimensional array, while modern radar systems have two-dimensional arrays with large number of elements. In case of ham radio, at higher wavelengths, only limited number of elements are possible and steerability will not be that high. 3 elements at the corners of an equilateral triangle has been used to steer the beam 120 degrees by manually changing the feeds. In the simplest form, a length of cable is used to produce the phase shift in the signals fed to the elements in ham radio. In one configuration, the phasing line used by VA7ST was 3/4 wavelength 75 ohms RG6 cable. 2-element vertical phased array for 40 meter has been used to direct the beam in one direction with strong directivity and forward-backward ratio. The spacing between the elements was quarter wavelength. DP-DT relays can be used to switch connection between the vertical elements. The radiating elements were quarter wavelengths. Windom antennas are basically off-center fed dipole. As the Carolina Windom antenna is not center-fed, unequal currents exist in the horizontal radiating sections, unlike in the standard half-wave dipole antenna. This is what makes the vertically hanging portion of the coaxial feed line radiate RF energy. Carolina Windom is thus an unbalanced antenna. M0UKD uses 10 feet of 50 ohms cable as the vertical radiator for his Carolina Windom antenna, which needs no tuner at 40 meter, 20 meter and 10 meter. He uses a 4:1 balance at the feed point of the OCFD. Unlike the half-wave dipole which is center-fed, they are broadband antennas to some extent. The original Windom antenna was fed 14% off-center with a single wire, which would radiate up to the operating position, which is quite undesirable. The Carolina Windom, on the other hand, uses a line isolator RF choke to prevent this. The part of the feeder between the antenna and the RF choke, which is hanging vertically above the ground, radiates, making the Carolina Windom an omnidirectional antenna. As this radiation is at low angle, it is suitable for DX work. Rybakov 806 is a vertical antenna supported by a telescopic fiberglass fishing rod, which gave it the name Rybakov, which means fisherman in Russian language. The suffix 806 is probably because it is a broadband antenna which can cover from 80 meter to 6 meter. IV3SBE, who designed it, describes it as a little miracle which is only 1.6 meter when not in use and 9 meter when fully extended and weighing only 2.2 kilograms. 8 meter wire is used with a 4:1 union at the feed point. Union by definition matches an unbalanced antenna to an unbalanced feed line. Here it is used to lower the impedance of a random wire antenna. Rybakov 806 vertical is a highly portable antenna popular for field operations. Though the length of the wire is not critical, resonance at bands of interest is avoided. As it is a non-resonant antenna, an antenna tuner is a must. Built-in antenna tuners of modern radios may be enough. A wire length of 7.6 meter can cover from 7 MHz upwards. If 3.5 MHz is needed, wire length has to be increased. Some sort of a ground or radial has been recommended. WB3GCK mentions a 25-foot radiator and a 25-foot radial. Extension of radiator to 53 foot for 80-meter operation was suggested. Slim Jim antenna, as the name implies, has a very slim design and hence very little wind loading. Jim stands for J integrated matching as it uses a J-type matching stub. Slim Jim antenna was described by Fred Judd G2BCX in 1978. The antenna has a lower takeoff angle and hence reported to have better performance than 5x8 wavelength ground plane antenna. People have made it using half-inch copper pipe, ladder line and many other options. Approximate gain in the horizontal plane has been mentioned as around 2 dBi. Slim Jim antenna should be insulated from the antenna mast with a free space of at least quarter wavelength. Antenna itself can be supported on a PVC pipe. Though it can be made for any band, it is quite popular as a 2-meter VHF antenna which can be made easily with good performance. It is almost like a vertical asymmetric folded dipole with a gap between the half wave and quarter wave regions. The exact feed points on the long and short parts of the antenna are determined by trial and error checking VSWR. After adjustments, the inner conductor of the coax can be shouldered to the longer part and sleeve to the shorter part. A crocodile clip can be used during testing to attach the coax inner conductor and sleeve to the antenna. Detailed descriptions and calculations for wavelengths ranging from 2 to 10 meter can be found at the web page. The page also mentions that View to RMU and many view hams could homebrew Slim Jim antenna just by using the described parameters even without the use of an SWR meter and get excellent performance. Random wire antenna, as the name implies, is a random length of wire suspended high above the ground, usually between buildings or trees. It is a simple way of going on the air quickly when the usual types of antenna cannot be installed fast as in the field setting. Random wire antenna is also sometimes called as long wire antenna, though it is not absolutely correct. A long wire antenna has to be at least quarter wavelength or better 1 full wavelength of the operating frequency. Wires at even multiples of quarter wavelengths will have very high feed point impedance which cannot be matched with an antenna tuner. Hence, it is important to avoid even multiples of operating wavelengths, though it is called a random wire antenna. An important disadvantage of a random wire antenna is that the wire radiates up to the point where it reaches the antenna tuner. This would be picked up by the metallic parts of the radio and any attached devices and can give you a burning sensation when you come in contact with them. This becomes more as the power output is increased and may be significant at 100 watts, though it might not occur at low power. Random wire antenna needs a good earth ground, which could be a cold water pipe if you are in the lower part of the building. If the shack is located higher up, a counterpoise is needed. Counterpoise is just a long insulated wire attached to the ground connection of the antenna tuner. Ideally, it has to be quarter wavelength of the lowest operating frequency. As it is quite long for 80 meter, it can even be looped around. Counterpoise will balance the antenna system from an electrical standpoint. Random wire antenna is sometimes deployed in a zigzag fashion if there is space constraints. But this will reduce effectiveness and make theoretical analysis quite difficult. Isotropic antenna is a theoretical antenna which has a perfect spherical radiation pattern which is never practically achieved in any antenna. Many commercial vertical antennas mention their gain in dBi in comparison with the theoretical isotropic antenna. They have a 360-degree disc-like horizontal radiation pattern towards the horizon all around, unlike the spherical radiation pattern of an isotropic antenna. Dipole has strongest signal radiation perpendicular to the orientation of the radiating element. Radiation from a dipole is weakest from the ends of the radiator. Hence, a dipole has a gain of 2.15 dBi compared to the isotropic antenna in the direction of the main lobe. Gain comparison with the dipole is designated as dBd. Gain expressed in dBd will be 2.15 dB lower than a gain expressed in dBi. Polarization of an antenna is the direction of electric field produced by the antenna. This would determine the direction of transmission and reception of the antenna. Usual antennas have linear polarization, which could be vertical or horizontal depending on the plane in which electrical field of the antenna oscillates. There is also circular polarization in which the radio waves rotate as the signal propagates. If it rotates to the right, it is known as right-hand circular polarization RHCP, and if it rotates to the left as left-hand circular polarization LHCP. I have come across these terms being used by radio amateurs who work through ham radio satellites. Signals from a horizontal dipole will be horizontally polarized, while that from a vertical dipole will be vertically polarized. For propagation by line of sight or ground wave, the polarization will not change during propagation. So, receiving a vertically polarized signal using a horizontally polarized antenna would give poor results. But reflection from the ionosphere in case of sky wave can change the polarization. Whip antenna is a common sight on four-wheelers these days, as most of them have a built-in radio, often covering FM and AM broadcast stations. Whip antenna is named so because it is flexible and hence has the movement like a whip when flexed. In some antennas, the active element is inside, while in yet others you can see a wire spiraling over a fiberglass rod. Popular rubber ducky antenna of handheld VHF and UHF amateur radio are whip antennas. Inner portion of the rubber ducky will have a helical springy wire which makes it flexible as well as cancels out the capacitance of a shortened antenna with its inductance. Most common type of whip antenna is a quarter wavelength antenna. They can be electrically shortened using a loading coil up to 1/10 of a wavelength. Longer 5x8 wavelength whip antennas can be designed for better performance with maximum possible gain in this configuration. Whip antennas are omnidirectional with equal radiation in all directions perpendicular to the axis of the antenna. Radiation from a vertical whip antenna is thus vertically polarized. In case of whip antennas mounted on a vehicle, the metallic body of the vehicle acts as the ground plane. Cobweb antenna is a small, lightweight, multiband antenna typically covering 5 ham radio bands from 14 MHz to 28 MHz. Cobweb antenna requires only one support and gives performance like a full-size dipole on 5 bands 20, 17, 15, 12 and 10 meter. Moreover, it can be fed by a single 50 ohms coaxial cable. It has a horizontally polarized radiation pattern. There are 5 folded dipoles which are fed by a common balun. As it is an omnidirectional antenna, an antenna rotator is not needed. Size of 5-band version will be only 2.8 into 2.8 meter, which makes it quite popular. 7-band version including 40 meter and 6 meter are also there. Cobweb antenna gives a reasonable performance at even 10 feet height, though 20 feet height is desirable. Another advantage mentioned is that as it has the appearance of a washing line, acceptance by the ham's family is good. As the dipoles get folded into square shape, impedance is around 12.5 ohms and needs a 1:4 current balance in the terminal box. When a current balance is used, no additional choking on the coax is needed. Log periodic antennas are typically used for VHF and UHF frequencies. It is also known as a log periodic array and is a multi-element directional antenna designed to operate over a wide band of frequencies. Log periodic dipole array is a common type of log periodic antenna which consists of several half-wave dipole driven elements. They are of gradually increasing length and mounted close together in a line and connected in parallel to the feed line with alternating phase. Thus, it simulates a series of Yagi-Uda antennas tuned to different frequencies connected together. But the Yagi-Uda antenna has only a single driven element, while all elements in a log periodic dipole array are driven elements. Other elements in a Yagi-Uda antenna are parasitic with one reflector and several directors. While Yagi-Uda antenna has a very narrow bandwidth, log periodic dipole array has a large bandwidth. While adding elements to a Yagi-Uda antenna increases its directivity and gain, adding elements to a log periodic dipole array increases its frequency response or bandwidth. Log periodic antenna has the same radiation resistance, SWR, gain and front to back ratio across the frequency range for which it is meant. Elements of a log periodic dipole array are pairs of metal rods fixed on a boom. Spacing of the elements follow a logarithmic function of the frequency. Length of successive elements and spacing between them gradually decrease along the boom. Helical antenna, as the name implies, is an antenna in which one or more conducting wires are wound in the form of a helix. It is typically used in VHF and UHF ranges, with the most common example in amateur radio as the rubber ducky of handheld radios. Helix can be found inside the rubber ducky when the outer covering is removed. If the helical antenna is made of a single wire, it is called monofilar, and bifilar if it has 2 wires, and quadrifilar if it has 4 wires. Helical antennas can operate in normal mode as broadside helical antenna or in axial mode as end-fire helical antenna. In the normal mode, diameter and pitch, or the distance between successive turns of the helix, are small compared to the wavelength. They function like electrically short dipole or monopole equivalent to a quarter wavelength vertical antenna. The inductance of the helix acts like the loading coil for electrically shortened dipole antenna. Normal mode helical antennas have maximum radiation at right angles to the axis of the helix and they are omnidirectional. Rubber ducky is the typical example of a normal mode or broadside helical antenna. Being electrically shortened antennas, gain and range of communication of rubber ducky is less than that of a full-sized antenna, as every ham radio operator is fully aware. Monofilar helical antennas have linearly polarized radiation pattern parallel to the axis of the helix. Bifilar or quadrifilar helical antennas can have broadside circularly polarized radiation pattern. Diameter and pitch of the helix are comparable to the wavelength in axial mode or end-fire helical antennas. These are directional antennas radiating off the ends of the helix along the long axis of the antenna. Radiation pattern is circularly polarized, and end-fire helical antennas are used for satellite communication as the antenna illustrated here. As you can see, there is a ground plane reflector at the base of the antenna. Small magnetic loop antennas can be used both indoors and outdoors. They are cheap, easy to build antennas which have been used for even DX contacts with an indoor antenna running 50 watts for CW, PSK, JT65 and FT8 modes on 10 to 40 meters according to K5IJB. Wide-spaced variable tuning capacitors which prevent arcing are needed when planning for higher power. You may be aware that the spacing in question is between rotor to stator elements and not between stator elements, and there are formulas for calculation of the minimum spacing required for a given voltage. Small loop antennas are small in comparison to the full wavelength of the transmitting frequency, but they are much larger than the small receive-only loop antennas which you may have seen supplied along with broadcast receiving sets. In its simplest form, a magnetic loop antenna is a loop of wire with an RF current flowing through it. RF magnetic field generated by the current gives electromagnetic radiation just like a dipole antenna. Analogous to the electrically shortened dipoles, the inductive reactance of the loop can be tuned out using a capacitor placed across the gap in the loop. The magnetic loop antennas has a reception null on the broad side. At least some of you would have noted this type of null in case of small AM broadcast receivers with ferrite rod antenna. When the end of the ferrite rod coil is pointed towards the radio station, the signal drops. This principle may be useful in finding the direction of transmission as well, maybe in a fox hunt. When the magnetic loop antenna is used indoors, the magnetic loop is placed at least 5 feet away with null side facing the operator. While a vertical dipole gives vertically polarized radiation all around, horizontal dipole gives horizontally polarized radiation. But it is difficult to implement a vertical dipole for lower bands like 80 meter, which will have to be more than 40 meter high. Horizontal dipole, on the other hand, has a null for signals on the ends. A magnetic loop antenna placed horizontally has no such null in the horizontal direction and gives a horizontally polarized radiation. Yet, most implementations of magnetic loops are in a vertical position for convenience of mounting. Magnetic loop antennas can be made in various shapes like circular, octagonal, hexagonal, square or triangular. An online calculator for an octagonal small transmitting loop antenna using conductors in the form of pipes is available. When the circumference of the loop, diameter of the conductor, operating frequency and transmitting power are submitted, the values for antenna efficiency, bandwidth, tuning capacitance, capacitor voltage and a whole lot of other useful information are displayed. They also mention that for highest efficiency, the conductor length for a small transmitting loop antenna should be greater than 1/8 wavelength. The conductor length should be less than 1/4 wavelength for avoiding self-resonance. Different methods for impedance matching in case of magnetic loop antennas are capacitive using additional fixed value capacitors, inductive tap like an auto transformer from the loop, and coupling loop using a small loop within the main magnetic loop. Of these, coupling loop seems to be the most tried out one. Some have even combined capacitive matching for additional bands in case of coupling loops as well. Small loop antennas are less sensitive to picking up electrical noise in the near field, typically less than 1 wavelength. This might be a boom if you have nearby electrical equipment which generate electrical noise, which is quite common in modern living spaces. This could be the reason why they are called magnetic loop antennas. A small magnetic loop antenna responds mostly to the magnetic component of the electromagnetic wave and is fairly insensitive to the electrical field component. So they are able to receive weak signals out of the ambient noise. K5IJB has given designs of small magnetic loop antennas built of LMR 400 coax cable. Variable capacitor is used for tuning and a smaller coupling loop is used for matching. It does not require a counterpoise or grounding. Ferrite beads are inserted on the antenna end of the feeder line to prevent common mode current. A version for fixed operation uses a 9-foot circumference loop on a fixed stand, and a portable operation version uses an 8-foot circumference loop with a breakdown stand. Fixed operation version covers 10, 12, 15, 17, 20, 30 and 40 meters. Portable operation version with 30-inch diameter covers 10, 12, 15, 17, 20 meters. Many of you would have seen children play with Slinky toys which are spring-like as illustrated in the picture. Slinky dipole antenna uses helical springs to have it shortened so that some have mounted it in attic when there was no way of having an external antenna. N1FDX used a Slinky dipole with a 1:1 balance and a remote antenna tuner located at the antenna. He could remotely control the tuner from his radio sitting in his shack. He had used the antenna in different configurations, including horizontal dipole, vertical dipole, and as small as 5 feet per side. He could tune it from 80 meter to 6 meter and even 160 meter. He could make numerous contacts throughout United States as well as west coast of Europe on 20 and 40 meter. 100 watts would be the typical maximum power which can be used in such locations, as higher power could heat up the surrounding nearby structures and cause damage to them. One recommendation is that the antenna may be no more than a quarter wavelength and could be much shorter. Instead of using an antenna tuner, the Slinky dipole antenna can be tuned by shorting out a few coil windings with aluminum clips. People have passed a nylon rope through it to support it in a horizontal position. A commercial Slinky antenna coil has 67 feet of spring and is very short when compressed. Diameter of the coil is small compared to the wavelength and the length of the coil. Typically, it can be stretched into a helix as long as 15 feet without becoming deformed. The original US patent granted in 1974 was as a tunable spiral dipole antenna. The patent for the tunable spiral dipole antenna expired in 1991. A coaxial cable can be used as the feeder while using the Slinky dipole as a resonant monoband antenna, usually on 40 meter. If it is being used as a multiband non-resonant antenna, twin lead or ladder line is used along with the tuner. Turnstile antenna is also known as crossed dipole antenna, as it consists of two identical dipole antennas mounted at right angles to each other. Currents fed to the dipole are 90 degrees out of phase. Just like the helical antenna, turnstile antenna can have a normal mode in which it radiates horizontally polarized electromagnetic waves perpendicular to its axis, and an axial mode in which it radiates circularly polarized electromagnetic waves along its axis. Circularly polarized antennas are useful for satellite work in VHF and UHF bands. It may be noted that the satellite tumbles and spins in orbit so that the orientation of its antenna changes during a pass. An antenna with circular polarization will not be sensitive to the orientation of the satellite antenna in space. A horizontally or vertically polarized antenna, like a usual dipole or monopole, will not be able to receive the weak satellite signals when the satellite antenna is oriented the other way around. While operating in the normal mode, the radiation patterns of two horizontally polarized dipoles produce an almost omnidirectional radiation in the horizontal plane. If several turnstile antennas are stacked vertically, the gain in the horizontal plane can be enhanced while reducing the radiation in the vertical direction. This is an obvious advantage in case of antennas used for television transmission. That can also be used as omnidirectional antennas for VHF and UHF transmission in amateur radio when one is not planning to work satellites. When turnstile elements are stacked, they are separated by half wavelength and the corresponding elements are fed in phase. In axial mode, radiation on one end is right-hand circularly polarized and that on the other end left-hand circularly polarized, determined by the phase of the feed connections. Turnstile antennas in axial mode can be made more directional by adding a reflector to prevent radiation to one side. A simple reflector is a passive set of cross dipoles as seen in the antenna by SV1XV. Reflected waves will be 180 degrees out of phase and reflection reverses the polarization. Hence, they can reinforce the forward radiation. For this, the reflector is placed at quarter wavelength behind the active elements so that the direct and reflected waves are in phase and add on. This provides a gain of 3 dB. The two dipoles in a turnstile antenna are fed with signals which are 90 degrees out of phase to each other. This is known as quadrature feed. It may be noted that 90 degrees is 1/4 of a sine wave cycle, which is 360 degrees. Two figure-of-8 radiation patterns of two dipoles, when combined, appears like a clover leaf pattern which is almost circular. Phasing line is typically a quarter wavelength coaxial cable.